Welcome back to section 1.3, where we're working on calculating limits more precisely. In this middle video, we're going to talk about something about indeterminate limits. So these are limits where we can't just plug in an x value like we were doing in our first video. And so we need a different method to calculate these. So we met one example at the end of the last video that was sine x over x, where we could not plug in our x value and calculate something that made sense. That issue happened because we ran into a 0 in the denominator. Now there's some other issues that might come up along the same lines. Here's another example of one where if I try to plug in x, I'm going to get a 0 in the denominator, because I would do 1 minus 1. But what would you get in the numerator? Let's just see. You'd get 0 also in the numerator. Now, one of the things that this means is that this function is not continuous at x equals 1. It turns out it's got an asymptote there. And so, yeah, plugging in 1 doesn't work because it's not continuous. But this 0 over 0 thing, sometimes people look at that and they want to say, well, any 0 divided by anything, that should be 0. Well, 0 divided by 1 or 2 or 3 or 4, certainly that is 0. But 0 divided by 0 doesn't make any sense. Neither does 1 divided by 0, or 5 divided by 0, or any number divided by 0. How do you take 5 things and divide it into no parts? That's not physically possible. So we're going to need a different method to deal with this one. Turns out that there's a way we could simplify this function that will help us calculate our limit. If you're looking at the numerator, you might have noticed that we can factor it. So if I wanted to factor that numerator, I'm going to need a 2x and x in order to get the 2x squared I need at the beginning. And I'm going to have either a positive 3, negative 1, or negative 3, positive 1 in order to make this work out. Turns out that what I need is a positive 3 here and a negative 1 here, and if you check that by multiplying, you get 3x minus 2x gets me that 1x in the middle. So now I've got x minus 1 both on top and on the bottom, and I can cancel them. And so now I'm just left with the limit as x approaches 1, 2x plus 3, and that looks like something I could plug in. That's just 5. So we did a little bit of simplifying of our function to start off with, and then we were able to plug in an x value. And that's a way we're going to do a lot of problems like this. When we run into this 0 over 0 issue, we'll be able to factor something and cancel. So this method is referred to as canceling limit method. The key to making this work is that the two functions, the original function that we started off with, this is in factored form, but it is the same original function, and the function we ended up with, the one that's just 2x plus 3, those two functions are exactly the same everywhere except at the point x equals 1. The first function, f of x, it has a hole at x equals 1, and g of x doesn't. G of x is just a line. But at all the other points, they're exactly the same. Well, that also means that their limits will be exactly the same, because a limit doesn't care what's happening at the point x equals 1. It only cares about what's happening close. And close to x equals 1, these two functions are exactly the same. So that's important enough that we've made it into a theorem, and it says that if I have a limit of g of x, and f of x and g of x are the same, except possibly at our limit point, then their limits will be the same. So just exactly like what we had up here, where I have two functions that are the same everywhere except one point, then their limit at that one point should be the same. Now, we called this section indeterminate limits. The reason we did that was, you noticed when we tried to plug in that 1, in our first problem, we ended up with 0 over 0. And the reason it's called indeterminate is because all the limits that show up as 0 over 0 don't always have the same answer. So, keeping in mind that canceling trick, if I look at these two limits, both of them, if I just try to plug in 1, would get me 0 over 0 if I just plug in 1. However, in number 1, if I cancel something, I've got these x minus 1s, I can cancel 1 on the top with what's on the bottom. Then I'd be looking at the limit as x approaches 1, x minus 1, and that's 0. So there's my final answer for that one. On this second one, on number 2, if I look at the limit as x approaches 1 after I cancel, I end up with just 1/2. And remember, the limit, if I don't have anywhere to put in an x, I just say it's 1/2. All right, so we had two limits. They both started off looking like 0 over 0, but they had different answers after we canceled. That's why it's called indeterminate, because this 0 over 0 doesn't give us any information about what our final answer is going to be. So please never, never, never make 0 over 0 your final answer. Also, don't make it 0. In the first problem, it did turn out that the answer was 0. That's possible. But in the second problem, the answer wasn't 0. And in fact, the answer could end up being any number. So let's do a couple of examples. The first one I think will be fairly straightforward. It's just a matter of we have to remember how to factor. The second one might need to remember a little bit of stuff from some previous classes before that would make sense. So in this first one, if I wanted to factor, I know that I'm going to need a 3x here and an x here in order to come up with my 3x squared. And I know that I've got to have a positive 2 and a positive 1, or a negative 2 and a negative 1. Since I know that I need a negative 7, I think I'm going to need a negative 2 and a negative 1, because otherwise everything in sight would be positive, and there'd be no way to get that negative 7. So, turns out that I need negative 1 and negative 2 here, because that way when I multiply these two, I get negative x. When I multiply the 3 and the negative 2, I get negative 6x, and that together gives me my negative 7x. Now in the denominator, I don't have x minus 2. I have 2 minus x. So in order to be able to cancel something, I'd rather have an x minus 2, because I can only cancel things that match. And it turns out, if you notice, this has exactly the opposite signs of the 2 minus x that we started off with. This was a positive 2 and a negative x, and this has a positive x and a negative 2. So the way we fix that is we just factor out a negative 1. If I factor out a negative 1, then I have my x minus 2's and I can cancel them. And now it looks like the limit as x approaches 2, 3x minus 1 over negative 1. And then I can just plug in 2. 3 times 2 minus 1 over negative 1 for a final answer of, let's see, that's 5 on top and a negative 1 on the bottom, so negative 5. I want to add a page in here to do the next one so that I don't run out of room. So for this number 2, again, if I tried to plug in 9, if I just tried to do square root of 9 minus 3 over 9 minus 9, I'd end up with 0 over 0. But I don't really see anything to factor here. So we're going to use a slightly different trick. You might have met in pre-calculus the idea of rationalizing a denominator where you were trying to get the square root out of the denominator. What I'd like to do here is rationalize the numerator instead of the denominator. And I know that sounds kind of strange, but what it's going to do is it's going to move us to a point where there is something we can cancel. All right, so in order to rationalize a denominator, you multiplied by the same numbers, the same square root and the same number, but instead of a minus, you put a plus. So we're going to use that same trick, where I multiply by square root of x plus 3. Now, since I've done that in the numerator and the denominator, I'm really just multiplying by 1, and I haven't changed the value of my function. I'm just going to change the form of it. All right, so that's going to get us to, we're trying to calculate limit as x approaches 9. I'm going to multiply on the top, but not on the bottom, and you'll see why in just a moment. So if I multiply on the top, I have to multiply the 2 square root of x's, and that gets me just an x. And then I have to multiply the inside and the outsides, so that gets me minus 3 square root of x plus 3 square root of x, and finally I multiply my last ones and I get a minus 9. And I'm going to leave my denominator factored. That's going to be to my advantage here in just a second. So this minus 3 and plus 3 square roots of x, those cancel out. And that's a good thing now, because it means that what I have left is just x minus 9. And oh look, there's an x minus 9 in my denominator. That's why I didn't want to multiply the denominator out, was I knew I'd be able to cancel these after a bit. Alright, so that gets me a limit. X approaches 9, 1 over square root x plus 3. So that's just 1 over square root 9 plus 3. And that's the final answer of 1 over 6. So it's still ultimately a canceling problem. It's just that I had to do this little trick to start off with, where I rationalized the numerator of my function to get rid of that square root and get me to a place where I could cancel something. All right. Now I want to point out that there's still a couple of sections that we haven't, a couple of limits that we aren't able to compute just yet. There's a couple of examples sitting here, and those will come up in later sections, okay? So this first one, if I plug in 0, that would still be a 0 over 0 limit, but it's not something that we can factor. So it's not something we can do in this section. In the second example, if you plugged in 2, you'd end up with 6 over 0. And again, there's not something to factor and cancel, so that's not going to work for us. We've only managed to deal with a sort of special collection of these 0 over 0 ones that we can in some way, shape, or form cancel. And in future sections, we'll be able to talk about how to do some of these others. So I want to revisit the difference quotients that we met briefly in section 1, because calculating the limit of a difference quotient carefully and precisely is really all about this canceling stuff that we just started talking about. And let me go ahead and add another page here. So I'm going to start off with the first one, number 1, and that one has its function 2x plus 5. So in order to calculate this difference quotient, we're going to have to do some plugging in to that function 2x plus 5. So when it says f of 2 plus h, the 2 plus h is what we put in place of the x. So that means we're going to have to do 2, and then instead of x, we put the 2 plus h, and then plus 5. So that takes care of the f of 2 plus h part. And then we have to subtract f of 2. So I might come off to the side and find f of 2 here and say, well, that's 2 times 2 plus 5. So that means that I'm going to need to subtract 9. And then all of that has to go over h. That 9 right there, that's what goes for our f of 2, because we came off to the side and figured out that f of 2 was just 9. All right, so we want to calculate this limit. So I need to distribute the 2. I get 4 plus 2h plus 5 minus 9, all of that over h. And so that is the limit as h approaches 0. Got some like terms going on here. 4 plus 5 minus 9. That actually all cancels out, because 4 plus 5 makes 9, and when you subtract 9, you end up with 0. So now I'm down to just 2h over h. And now the h's cancel, and so I'm down to the limit as h approaches 0 of 2. So this is one of those strange ones where my limit function doesn't have anywhere for me to put an h. So I don't have to do any calculation. I just say that my final answer here is 2. All right. So we just calculated the limit of a difference quotient, and you'll notice that the whole idea here was that these h's canceled out. To go back to the beginning for just a moment, the reason that I couldn't start off just by putting in 0 for the h is that I would have ended up with f of 2 right here, subtract f of 2, that's 0, and a 0 in the denominator. So I already know that that's not going to work, and I'm going to need to simplify first and do this canceling before I can calculate the limit. So that was for number 1. We're going to follow the same process for number 2. So I'll copy number 2 down here so that we can not have to scroll too much. We're going to be finding the limit as h approaches 0, f of, I believe this one's negative 1 plus h. Negative 1 plus h minus f of negative 1. Divide by h. And for this problem, f of x is 3x squared minus x. Okay, so I know that I'm going to need to find f of negative 1. So that's going to be 3 times negative 1 squared minus negative 1. So that's going to end up being positive 3 plus 1, so that's 4. So I know that when I have this f of negative 1 here, I'll be able to put in 4. But I also have to do the f of negative 1 plus h. And that's the one that I have to think a little bit more carefully about. So f of negative 1 plus h. I have to watch out, because in my f of x, I have this x in the parentheses, and it matches these x's over here. But down here, I don't have x in the parentheses, I have negative 1 plus h. So that means that everywhere I see an x in the original function, I have to put a negative 1 plus h. So 3, and not x anymore, I'm going to replace it with negative 1 plus h squared. And then minus not x, but negative 1 plus h. And so that'll take care of this f of negative 1 plus h part. We still have to subtract the 4 that we said was our f of negative 1 here. And then we're going to divide everything by h. So we know we're going to need to do some simplifying. Going to do our exponents first. So 3 times negative 1 plus h squared is going to be 1 minus 2h plus h squared. If you need to expand that out, that's totally okay. And I'm going to distribute this negative through the parentheses. So that gets me plus 1. Sorry, I got a stray mark going on there. Minus h, and I've got this minus 4. All of that is still over h. So then I distribute my 3, so I have 3 minus 6h plus 3h squared plus 1 minus h minus 4 all over h. And once again, my numbers all end up canceling out. 3 plus 1 makes 4, and subtract 4 and I've got 0. So I'm down to, let's see, I've got a negative 6h and a negative h, so that makes negative 7h plus 3h squared over h. Now this is the most common place to make a mistake, so we're going to do this really carefully. My goal here is to cancel out the h on the bottom so that I can just plug in 0. However, I can only cancel things that are multiplied together. I cannot cancel an h right here because that's not multiplied by this 3h squared, it's only added. So the way we're going to deal with that is we're going to factor out an h on top. They both have an h. So this is negative 7 plus 3h. If I factor out an h, there's my h. And now I have a multiplication going on in the numerator, so I can cancel the h's. So now we're just doing the limit as h approaches 0 of negative 7 plus 3h. And so I can plug in 0. Negative 7 plus 3 times 0. And that's just negative 7. So I know these are not short problems. That one had several steps to it. But they're going to be very, very, very important, and they're in fact what's going to help us transition from limits to our next topic of study in this class. So please be sure that you're paying attention to these problems. I'm not going to make you do a lot of them because they are long, but be sure that you do enough that you get kind of comfortable with this process. That wraps up our section about indeterminate limits. We've got one more short video in this section about the squeeze theorem, and that'll wrap up this section.